Test, test. Actually, I'm not sure if I don't sound amplified, right? I mean, I'm not sure if it should be because there is a good reverb in here, but maybe I'm not being recorded. We might ask Karel. Yeah, actually, yeah. If someone can check it. So should I start or shall we troubleshoot first? Okay, great. So, good morning to all the brave people who managed to get here by 9 a.m. I'm going to give a presentation about QSAR, quantitative structure-activity relationships today. It's going to be educational, introductory lecture. It's going to be, of course, a little bit colored by my personal taste, but basically we will talk about straightforward, basic QSAR concepts. But first, let me briefly introduce myself. So who am I? My name is Dehaen. I'm employed at UCT Prague. Actually, on there I have a dual affiliation. You can see the logos here. I'm part of the Department of Informatics and Chemistry and part of the Department of Organic Chemistry. At the Department of Informatics and Chemistry, I do more or less all kinds of applied cheminformatics. I did my PhD there as well. In the Department of Organic Chemistry, I'm in Andrea Brancale's group, and there I do basically computational support for medicinal chemistry. And this means mainly structure-based virtual screening, drug design, and so on. So things like molecular docking, pharmacophores, such things. So what interests me, actually, I have very broad interests, but when it comes to chemistry and science, I'm particularly interested in cheminformatics, medicinal chemistry and computer-aided drug design, organic chemistry in general as well. I have actually a background in organic chemistry, and I'm interested in DSP as well, particularly of audio. So today's presentation, here's an overview. First, we will actually discuss, so what is QSAR, what is QSAR not? Then we will have a little historical overview. Where does it come from? What's the basis of it? Then we will return to something even more basic. We will talk about SAR without a Q. Then we will talk about what type of data we use in QSAR, how we represent molecules in QSAR, what type of typical methods exist, how we validate it, and we talk a little bit about the important notion of the applicability domain of QSAR models, as well as its interpretability and even explainability. Finally, I will mention very briefly a few applications just to warm you up for the tutorial that's going to be this afternoon. So, what's QSAR? I said it already. The abbreviation is Quantitative Structure Activity Relationships. Actually, often when we talk about QSAR, we talk about more than just activity. Often it can be any kind of property. So more correct perhaps would be to talk about QSPR, because for example you can also predict properties like aqueous solubility using QSAR type approaches. Sometimes also when you have a very specific property, it can get its own abbreviation. For example, in the fragrance field, they talk about QSAR because the activity is odor or olfactory. In one sentence, I would summarize the notion of QSAR as the combination of medicinal chemistry, physical organic chemistry, and statistics, which includes also, let's say, estimation and even machine learning. Here is an alternative definition, which I got from a paper of Tropša, where I would say it's quite in line with my definition. He calls QSAR, I'll read it out loud, an application of data analysis methods and statistics to developing models that could accurately predict biological activities or properties of compounds based on their structure. So very straightforward, put here in a formulaic way. More or less, the QSAR assumption here is the biological activity that you predict is a given function of the structure features plus a certain error. Okay, so here is a high-level overview of what is QSAR from beginning to end. I think in the next slide I have also some picture that shows the same thing. So maybe it will be easier to go through it with a picture. So First, we begin with a data set. So this means we have a list of molecules or compounds. Well, it can even be chemical mixtures or salts or something like this, but let's say we have a list of chemical compounds and associated properties. So we need to somehow collect this, curate this, clean it up. Then when we have those, we need to calculate molecular descriptors. I will talk in detail about what those are, how we calculate them. But let's say there are certain numerical features that correspond to our structure. These get pre-processed. For example, if the descriptors are correlated or something, you can prune a few or correct for that. And then, okay, let's say we have a ready data set. So we did the first column, and the data set is now ready. So now we have to divide our data set into an honest train and test set. And what this means is the train set is what we build our model on. The test set is what we use to check if our model actually has real predictive value. The various ways in which this can be done will be discussed in a moment. Okay, let's skip a bit further. What is QSAR and what is not QSAR? You could call QSAR a form of traditional supervised machine learning. The QSAR traditionally is non-deep, where this is because in general, when you have chemical data sets, you have small data regime. So what does it mean, small data regime? Something like dozens to hundreds to perhaps thousands of compounds. Typically in bioactivity data, few thousands is the highest that you get, unless you get very noisy data like HTS readouts. Also, a typical traditional QSAR model will tend to have some interpretability to it because the estimators will tend to be rather simple. For example, when you have something like decision trees, actually you can have a look at those trees and understand what they are doing. Recently, people are using this term, deep QSAR, in their papers. It seems to me a little bit like a semantic distinction, whether they call it QSAR or not. It just means they use deep learning techniques, so they will use some neural networks that are not too superficial and where, let's say, inside of the black box it's also not so easy to see what's happening. Then, within QSAR, there is also virtual screening, or rather, when we build a QSAR model, one of the typical applications that we can use it for is virtual screening. It means, for example, we can use it to fish out activity. We can use it as property filters. For example, very typical is we don't want to have compounds that are likely to be hERG binders, so we can build a QSAR model for hERG and filter out the compounds that are the most likely to give problems down the line. Now, QSAR models are quite simple, and this means that we have issues of applicability domain, which now I will just briefly summarize as if you have certain molecules that are out of domain, that in terms of their features are very different from your training set, your predictions will simply not be reliable, and the model will not be applicable. Okay, now a little bit of a historical intermezzo. So I put for these 3 points of physical organic chemistry and statistics and medicinal chemistry, I put a few important dates. So the very earliest date, it's the method of least squares as developed by Legendre and Gauss. Then the earliest formulation of the relation between chemical structure and physiological action, which actually it's like surprisingly early. I think in the next slide I put a screenshot of this statement, which is quite ahead of its time. It was in the middle of the 19th century, so even then, this idea that the chemical structure somehow determines the function of, in this case, a poison form to the Hammett equation. That's the let's say, one of the elementary early formulations of QSAR, and that's the hunch equation. And you can see here, actually, you have this here above, this linear formulation where D, that's some descriptor, can be something like a log P, partition coefficient with fitted constants, and this then correlates with the activity, or rather the logarithm of the activity. See here, that's some property of interest. Actually, if you read these hunch papers, it doesn't have to be linear. You can see here, you have some polynomial here, and also what's interesting to see is this thing here. So this sigma, that's actually one of these Hammett constants. So this makes the connection with the previous slide. Okay, then what's also important, that's the Free-Wilson formalism, and we can summarize this as the concept that you have something like a sum of substituent contributions, where you have something like, let's say, baseline activity, and then based on some functional groups or some, let's say, chemical patterns that you add, you have something like a sum of linear contributions. For example, when estimating log P, typically this is done in fragment per fragment or atom per atom sum. Then also I should mention in this historical overview, COMFA, that's the first 3D QSAR. It's actually rather expensive, comparatively expensive method where you make a sort of grid or map, you place conformations in there, and then you can use this for forward screening, property prediction, and so on. Now, QSAR is actually used in regulatory context. So the OECD has guidelines, and these are actually used when doing risk assessments of compounds. For example, there will be models for persistence in the environment, risk of toxicity, and so on. And because it's in a regulatory context, actually, there it's very important to know where are the limits of the model, how far the model can be taken, and where the model will not be reliable, because they're actually used to control which limits do we put on what. So they have some nice principles for what a QSAR model should have. So they should have a defined endpoint. Here also they are strict. The algorithm should be not vague. It should not be a black box. Likewise, because it's regulatory usage, the applicability domain needs to be really strictly, unambiguously defined. Likewise, there need to be good metrics on how good actually the model is. If possible, mechanistic interpretation is great, but sometimes that's not possible, especially if the underlying biological activity is something quite complex. Of course, it cannot be captured by some simple descriptors. Okay, now SAR, QSAR without Q. What does it actually mean? Structure-activity relationship. So first of all, it's non-quantitative, and this means something intuitive. It's something which is done by a medicinal chemist, and every medicinal chemist will do it in a little bit different way, but it's more or less the logic which is used to explore the properties around a compound. So now a quiz. Who recognizes this man you see here on the right? And I will give a tip. He was voted the third greatest Belgian. So greatest Belgian was Catholic missionary. Second greatest Belgian was Eddy Merckx, multiple Tour de France winner Eddy Merckx. And the third one is this father of SAR. So who recognizes the man? Okay, no takers. So this man is Paul Janssen of Johnson & Johnson fame. So in the SAR field, he is a true giant. He himself brought 80 drugs to the market. Actually, in those days, it was a little bit easier because even the framework of clinical trials wasn't established in the way that we know it now. And he is something like a figurehead of the trial and error approach, where you explore around molecule. Maybe you see, okay, what happens if you invert the ester, or what happens when you put certain substituents on the ring, and do basically gradual exploration of some compound. Here you see a very classic example, is the optimization of meperidine, relatively weak opioid painkiller, towards the now notorious fentanyl, which is highly potent, but at the same time clinically very useful, for example, due to short pharmacokinetics. Okay, now, when we build a QSAR model, we begin with getting data. So what are some data sources that we have? Very typical for bioactivity data is Campbell. When it comes to large data sets, there is PubChem, which will actually contain all kinds of information, including predicted information. There are community benchmarks, for example, things like sample, which will, for example, contain partition coefficients in certain solvents, and which are actually used as benchmarks to see what's the state of the art now, how predictive are current methods. In the literature, you will find all kinds of ad hoc data sets. For example, in medicinal chemistry papers, if there are 100 or 200 compounds, actually that's already a data set. There are also commercial databases that you can use. There is typically Axis and SciFinder. They contain mainly reaction data, but actually at the same time they also collect, let's say, physical data like melting points, boiling points. Actually, even it contains bioactivity annotation. You have to be a little bit careful with it, because as I put down here, when I was in a meeting with the SciFinder people, can I extract some data sets from your software? They got very angry at me and they said, no, you cannot do this. So yeah, so if you do that, maybe you can publish it. Okay, so before we use this data, often the data will have problems and we need to clean it up. Some of these problems we can fix, some of them are inherent to the data. For example, here, this quite recent paper, it points out some long time well-known issue, and this is that even within different IC50 or within different KI assays, actually the correlation of the data is really, really weak. You can see here the R2 is quite far from 1. Of course, it's a little bit exaggerated because the size of the points is quite big, but you can see that actually these are the same compounds, but different assays, so different IC50 assays, and you can see that actually when a different group measures it with their own assay, those values really don't correlate so strongly. Even more concerningly, you can see here this satellite line, and this actually probably is a data deposition artifact, because it means it's wrong by exactly 3 orders of magnitude. So probably they confuse millimolar with micromolar, or nanomolar with micromolar, something like this. So this is something which in a real QSAR application, always you have to deal with this. Often it needs looking at the data with your own eyes, seeing maybe which groups you consider reliable, which you don't. Sometimes between different depositors, you can do something like a correction, which will make the models also a little bit more accurate. For example, very typical in Campbell is if you have assays which are large-scale HTS assays, very often they are like automatically read out. They are not corrected. They didn't have orthogonal assays, and very often they can be even just compounds that interfere with the assays and they don't have real activity. Yeah. Also, one more thing I should remark there is here you see between IC50s already you have issues, but what is also sometimes done is just combining IC50s, KIs, KDs, EC50s, and so on. So that should not be done. These assays measure something different, and it also means that you can have many orders of magnitude difference, and in general also when you don't have any functional information, for example, whether a compound is agonist, partial agonist, inverse agonist, whatever. Okay, so that's when it comes to the biological numbers, but actually even with the molecules themselves, some cleanup is needed. So the first thing is actually molecular identity itself. So often you will have duplicates, and when you have duplicates, they maybe also will have different numbers. So you need to check somehow if these molecules are the same. And this is not as obvious as it seems, because sometimes the compound will be deposited as a salt, sometimes as its free base. If there are several tautomers, depending on which normalization algorithm the depositor used, it can be different as well. Likewise, protonation states can differ, and the state you will have at physiological pH may not be the same as what's reported in the paper, and so on and so on. So many ways in which deduplication is actually not that easy. And actually, all these factors, like which tautomer you have, which protomer you have, is dependent on which solvent you have, which pH you have, and even which temperature you have. For example, the barrier to convert between different tautomers, of course, it depends on the temperature. Or your likelihood of crossing it depends on the temperature. Then also there are even technical issues, like some cheminformatic software will be more permissive than others. And for example, there are certain smiles that can load in OpenBabel, but they cannot load in ABKit. For example, on Monday we saw such a smiles projected on the screen here. Then also it can be that some of our molecules have undesired properties. For example, if we want to follow up with docking, if you have metals in there or boron in there, many docking scoring functions, many force fields, they don't have those atoms parameterized, they don't know how to deal with them, so we should remove them while it doesn't cost us anything computationally. Then also in Campbell, for example, you can see this. Sometimes a chemical entity can be a mixture, or can be an extract from a plant, or can be diastereomeric mixture, of which we don't know what is the ratio. Can be even, depending on a data set, specific conformations only. Tropisomers can be even, well, not in Campbell, but can be even reactions, for example. So when it comes to the tautomer-protomer issues, let's have a look at some of these tricky cases. So for example here, the first two structures on the bottom, well, of course, they are just two equivalent Kekulé structures. But then up here, these tautomers actually, they are genuinely different species, because you can see that the hydrogen actually moved, and you have in total 3 of them. And in case of these spiridon type substances, actually which one is the major one, it's not so easy to determine. Likewise here, another typical example, you have this imidazole type heterocycles, where whether it's protonated or not is a little bit on the edge, and where it's going to be protonated, where the positive charge is going to be, is also something you can discuss. And then finally, you also have the issue that some things, according to tautomer enumeration algorithms, are tautomers, but actually in practice they will not interconvert. So actually, this line here, there should be a big X through it, because those two obviously don't interconvert. Now, here I call it featurization of molecules, but let's say how do we represent a molecule in a computer, extract features from it that we can use for building QSAR models. So we use for this something called descriptors, and one way to describe descriptors is they are graph invariants for a chemical graph. Now, chemical graph is something a little bit different than a simple graph, because the graph is colored. So this means that the vertices of the graph have, for example, atomic number. it's weighted. It means the edges we assign a bond order. It's non-directed, which is nice, but usually also for every vertex and edge, you will have extra data on there, like for example, the charge, which hybridization you assign it, and so on. So it's not quite a simple graph, so we cannot call them strictly graph invariants. So how can we call them invariants? Because they should be invariant to the vertex order of the graph. It shouldn't matter how we canonize this graph, but in some cases also they should be even invariant to rotation and translation, because a molecule's properties don't change depending on rotation and translation, at least as long as it's in, let's say, vacuum or homogeneous solvent. Then here another citation from Tropsha. There are 3 keys to the success of any QSAR model: building exercise, descriptors, descriptors, and descriptors. So very important. Okay, so which ones exist? There are many possibilities, but one highly typical thing is a fingerprint. So essentially we can call this a list or an array of descriptors that result from some common process. Usually this is a binary vector. Sometimes it can be also a count vector. Sometimes it can be also a vector of some continuous values. Typically these binary values, they correspond to the presence or non-presence of a certain structural motif. Yeah, for example, here with the binary descriptors, I give a few examples. I think maybe in some follow-up slides, I have some examples of it. Yeah, actually, I will. One of them, which is particularly important, which is called the Morgan fingerprint, I will describe in detail. So here, with the binary descriptors, we talk about, is it there, is it not there? In case of integer descriptor or a count, we just count how many times this feature is there. In some cases, it can make a model a little bit stronger. Okay, then when it comes to continuous descriptors, these can be things like calculated log P or some QM calculated properties, or something like distance to a certain target molecule or something like this. It can be even something that we actually measure and know, like for example some NMR shifts. Yeah, so often, as Professor Kirchmeier also showed on Monday, we categorize these descriptors according to their dimensionality. It's a little bit not quite 100% correct, because those things that are derived from the topology, from the connectivity of the molecular graph, we call them 2D, but actually a graph is dimensionless, so it's not 2-dimensional, it's 0-dimensional. Professor Kirchmeier discussed those, so let's skip over that and let's go to fingerprint example. So, yeah, I was just looking at the time, so we are at 9:30, so I should go a little bit faster. What's the ECFP? This is called also Morgan or Morgan-like fingerprint because it applies the variant of the Morgan algorithm, which is also used for graph canonization. And basically, it's a molecular fingerprint that encodes topological neighborhoods around atoms at a given threshold. It's very commonly used as input in QSAR. It's highly performant. It's highly generic. It's implemented in major cheminformatics packages like the CDK and ADKit and so on. Actually, the original ECFP implementation was in Pipeline Pilot. So let's see this example now. So we have this molecule here, O-methylproline. So how do we construct these environments that are shown here? So we begin at the radius 0. So every atom, atom 0 to atom 8, the first fragment we have is just the atom itself. We have certain graph invariants that we care about. So for example, we care about the atomic number, we care about the heavy atom degree, and we care about the amount of hydrogens. So, and here already we see that actually some of these fragments are identical, and they occur several times. So we will this will hash to the same number, and we will fold it to the same bit in our fingerprint, which I will show in the coming slide. Okay, so when we have these atomic fragments, now what we do is we extend those by also adding their directly connected neighbors to it. So for example, the atom 2 here, you can see it's this degree of 3 carbon atom. The next radius fragments will just have the directly connected atoms also included. So you basically have these 2 oxygens and a carbon on there, and you have inside of this fragment this ester functionality. Now, sometimes also you will have redundancies where, for example, you will have the same fragment but a different center atom, so those we remove because that's not extra information. We can keep on repeating this process by just taking the neighbors of the neighbors and the neighbors of the neighbors of the neighbors and so on until we reach the radius that we want. Okay, now how do we get this into a fingerprint? When we have the atomic fragments, it's easy. We take some atom properties we care about. So here in this case, it's atomic number, 6, carbon, heavy atoms that are connected, just 1, and amount of hydrogens that are on there. This is a methyl, CH3, so that's 3 of them. We take this number and we apply some hash function. Doesn't actually matter which one, as long as it projects the number nicely and randomly over, for example, 32-bit space. Then when we have those numbers, now here we can generate new invariants by hashing the numbers of the neighbors. And then we get new numbers that correspond to these fragments. So now we have a system where we have some number that corresponds to each of these neighborhoods. Once we have those numbers, we want to fold it into a fingerprint, and typically this is just done by a modulo operation. So you take this big number, and you make sure it fits into the size of your fingerprint. Here, as an example, it's shown as a 64-bit fingerprint. In practice, an ECFP will rather have 1024, 2048. Okay, so another example of how an ECFP works. So this is the one slide summary of what's inside of an ECFP. Actually here, these are real numbers. Those are the actual numbers generated by the Ardikit Morgan fingerprint. And what you see here is the molecule we encoded. That's this 1,1,1-trifluoromethylthioethane. And you see here the radius 1 atomic neighborhoods. So they are just atoms, fluorines, carbons, sulfur, and so on. Here we see the radius 1 neighborhoods where you have the neighboring atoms also included. And then finally here you see the radius 2 atomic neighborhoods. In such a small molecule, actually you can see that these fragments tend to contain even almost the entire molecule. We take the identifiers of these fragments and we just hash it. We hash it into a bit vector. And this then has a really nice form to put into QSAR model. Okay, so now, before we can start modeling, also we have to do feature normalization. Very often, descriptors are correlated and we need to correct for it. Sometimes also we may want to combine different fingerprints and different descriptors where our model architecture may not be ready to deal with that, or will give outsized influence to descriptors where the range is just larger. Some features will be just irrelevant. They won't have any relation with our endpoint of interest. And of course, it should be remarked, the fewer features we have, the faster it is to train our model, and usually also the more interpretable is our model. Okay, some ways to correct for this correlation issues is if there is collinearity, if the R-square between the descriptors is too high, we can just throw them out. Depends on which estimator we use. For example, for random forest, it doesn't really matter if you have a lot of correlated descriptors. For other methods, like for example, naive bias classifier actually is very important. When it comes to outsize range of descriptors. For example, we can do normalization by using z-scores or even just scaling between 0 and 1 by taking the minimum and maximum of the descriptor, although then it means that we have dataset-specific range. Yeah, so when it comes to feature selection, deciding which ones we keep in there and which one we remove. Sometimes you can build a model and actually learn from it directly what are the feature importances, and then you can just prune out the irrelevant stuff. You can do also things like PCA, principal component analysis, and have a look what your first principal components look like, remove the irrelevant ones, or combine several descriptors into one. You can also do experiments where you leave one or several descriptors out and see what's the influence there. Okay, training a model. Once we have our feature selected, typically we use really standard, by now one would call them basic, old school machine learning algorithms, and even simpler estimating methods like logistic regression, for example. So usually when you use some let's say contemporary modern neural network architecture, it's already not called QSAR anymore. As I mentioned, typically QSAR is supervised learning. You have an endpoint. So unsupervised learning, that's not really QSAR, but still sometimes you will do clustering. For example, if you want to do dataset splitting. But what's important is that in QSAR as well, there is a difference between classification and regression. Simply put, in classification, the endpoint is a category. For example, active, inactive, or active at this receptor, active at that receptor. In the case of regression, we just have a continuous endpoint. For example, some outcome of an assay, or solubility in water, something like this. Yeah, so there are some linear approaches, and in some cases, actually, it's enough. But all the rest tends to be nonlinear to some extent. So here is just an overview of typical methods that are used actually in practice for QSAR. So you see here there's also a neural network in here, but in QSAR it will be something like quite shallow MLP. I see also, I just put one tree-based approach in here, which is a random forest. Nowadays gradient boosting works a little bit more, so it's a little bit more recommended. Similarly for classification, these typical methods are listed here. So yeah, so clustering, which is not really QSAR, you can basically, depending on what your data looks like and what you want to see, you can decide, let's say, for example, if you have quite globular data, you can decide to use k-means, or if you have unconnected groups like here, you can pick an appropriate method like dbScan or something like this. Okay, so now an example, because we will use it in the tutorial, the random forest. So what is a random forest built from? It's an ensemble model built from several decision trees. And a decision tree that's very straightforward. It's typically binary, and you basically, you look at your descriptors. So here, that's called D1, and you just make something like a binary choice. If this is a continuous descriptor, for example, okay, let's say this is log P, depending on whether it's higher or lower than some number, you go to different side of the tree. Or in case you have a binary fingerprint, it's even easier. Whether there is 1 or 0, you go to the left or you go to the right. And actually, these tend to be already quite powerful, and they are also quite interpretable. But there, frequently, you have the issue of individual decision trees being subject to overfitting problems. And actually, it turns out that if you combine them in a smart way, you can build quite performant models. For example, here you can see that actually what is done here is so you have your training set, certain amount of molecules that each have n descriptors. Then you build a certain amount of individual decision trees. Often you will take only subset of molecules and subset of features. You build a bunch of decision trees, and then you combine them somehow. You use some kind of consensus For example, here, majority voting is used as the consensus method, and then you have the final classification is probability. So when we train a model and when we check how well it performs, we have to do accurate data splitting. How come we have to do it? If we didn't do it, we could build a tautological model where we would have total overfitting. For example, you can see here in this classification task, most likely there's a little bit of noise in here. You can see here what would be like the expected fit, where there will be a little bit of misclassification, but this is a nice, simple splitting on the 2D plane, whereas here it's just like the data completely determines how the fit is done here. Same thing for regression here. Most likely there's a little bit of noise from various sources on there, so a simple fit will make more sense than just curve fitting, so that exactly the noisy data fits on there. So, so this means we have to split our data and make the task a little bit more challenging. For example, here is in an overview some k-fold splitting. K-fold splitting is done here, where basically what you do is first you have all your data. This you split up into training and test data, and then within the training data, you look at n folds, so 5 folds in this case. You build 5 models with each split, so that actually during the training you saw all the data anyway. This means you can optimize the parameters of your machine learning model, and then finally, when you optimize those, when you found the best point, only then you can apply it on your test data, so that you have honest numbers and no information leakage. What kind of splitting can we do in the chemical context? The easiest type of splitting, that's random splitting. But often it makes the tasks a little bit too easy, because you get similar scaffolds, similar descriptors, and so on in your test trace set. What can also be done is scaffold splitting. This is already a little bit more interesting. So it can show if your model has some little bit of generalizability, if you can hop between different scaffolds. Actually, that's not shown on the slide, but another typical thing is doing similarity split. That's one place where you could apply some clustering techniques, again, to see if your model can jump to predicting dissimilar compounds. Typically in a QSAR context, actually, that's not really possible. Then, final way to split, especially important in medicinal chemistry context, is the time split. So you basically modulate the discovery process where you build a model with the information that you would have had in, let's say, 1990, and you see if your model is able to predict the new data that came out, let's say, 10 years later in 2000. So when we judge how good a model is, there are metrics for it. I see that I don't have a huge amount of time remaining, so let me just show this many different ways, which from the confusion matrix, so that's here in red, pointed out from the true positive, false negative, true negative. From these 4 values, you can calculate a bunch of binary classification metrics, which, depending on what kind of task you have, actually different ones will be meaningful. For example, when you have a highly imbalanced data set, often something like accuracy will give falsely good performance, and you will rather want to use, for example, Matthew's correlation coefficient. Likewise, if you are building a model that you're going to use for virtual screening, actually you're interested in picking out the best compounds first, and not so much what happens somewhere in the middle of your data set. Likewise, for regression, there are many metrics. I will skip through these a little bit faster. Then, when it comes to interpreting models, sometimes a model is just naturally interpretable. In case of Hunch model, it's simple. Actually, all these factors, they have a clear meaning, and you just assign some weight for it. Some models are a little bit more like black boxes, but anyway, you can interpret them, for example, by probing them with slightly different inputs by changing one of the descriptors, for example. For example, if you have some fingerprint that corresponds to the presence of certain atoms or not, you can simply do leave one out experiments. Some models also offer just feature importances directly after the fit. For example, Random Forest does this. There are many tricks for this. I'll show them in the tutorial, and what's nice about them is that they are basically model agnostic. Not feature agnostic, but model agnostic. So, as we already discussed, so in a QSAR model, applicability domain is like important limitations. We need to make sure that we don't do predictions on compounds that are outside of the domain of applicability, where the compounds are dissimilar to our training set, because it will mean that the predictions are unreliable. There are various ways to look at the applicability domain. Like, for example, here there is shown Williams plot, where you have on the x-axis you have the leverage, on the y-axis you have the residuals, and you basically make a box within which you are willing to do your predictions. Likewise, you can take some centroid around all the descriptors you have, and only within that centroid you're willing to make those predictions. Then one typical issue is the issue of activity cliffs, and what this means is that on your let's say activity landscape, you will have compounds that are very similar, but they will have very different activity. And in a simple QSAR model, very often these will be sources of wrong predictions. It's also something like a SAR paradox, because they are very similar in structure, but they are very different in activity. So it's kind of contradiction with the idea of the function determines the structure determines the function, so similar structure determines similar function. Okay, so now let's conclude here by going through the most typical applications for which we may use QSAR. We can use it simply for virtual screening. If we have some big collection of commercial compounds, picking out the best ones that we can then follow up by purchasing them, testing them, or using more expensive techniques like docking or free energy estimation or something like this. Other things we may use QSAR for is optimizing other parameters, like, for example, certain ultimate endpoints, perhaps an anti-target, perhaps the potency at several receptors of interest. For example, very typical is when optimizing a compound, we don't only optimize its activity, but we also optimize its drug likeness and its synthesizability, which sometimes are estimated with these simple cheminformatic methods. Yeah, here is also another example of some what we can consider ultimate filters. For example, there is this really big TOX21 data set where was, let's say, a community effort to build models for various toxicity endpoints. And now, so an invitation, this afternoon we will do a QSAR tutorial. We are going to use open source software, mainly RDKit and scikit-learn. So RDKit for the chemistry side, scikit-learn for the estimation, machine learning side. We'll use Python. We will do this in Python notebooks. Actually, basically no previous knowledge is required. We construct the notebooks in such a way that they can just execute without thinking too much about it, but still a little bit of knowledge will be useful if you want to tweak it a little bit. And that's it from my side. So thanks to my funders, thanks for your attention. See you at the tutorial, and if you have questions, feel free to ask them.
Questions? You have 10 minutes. Everything was clear. Seems yes, so in this case,
I will have one. When you combine fingerprints with different characteristics of compounds, how do you choose scaling and tricks?
So actually, nowadays in practice, the way this is done is you don't do scaling, but you pick an estimator that doesn't care about this. But if you cannot do this, actually, what worked for me is z-scores. It's close enough, and something like a random forest can deal with it.
Some other questions? Oh, okay. Thanks, Lee.
Thanks.
Vylepšil jsem si ty takové ty soutěžní, víš co, takže když mi to přišlo zajímavé, a byla část, tak si říkám, jako víš co, tak jsem to jako podpíkoval, nějaké restriktory, jo, tak jsem to tam jako nerval. Někdy se to povedlo, a jednou se to moc ne, ale...
To je jakože to je, že ten kurz je přijde fakt dobře udělaný, že když se jakoby máš prostě nějaký předchozí znalosti toho, tak stejně prostě tam můžeš jako ještě se těch víc
hlavně jako to vysvětlené dost jako podrobně. A vidíš, že to jako nutí státní se jako jako víš co, chci říct, jsem nakonec nejde ideální svět, který doprava nebyl lepší, ale jako se dělalo.
nějaký činy, něco,
you have to include this in every national chemistry.
Did it work?
It works, but only for particular triangle structures, so they should be rigid, and they should require original structure.
Yeah.
So they should have a similar scaffold, or the same scaffold, because it based on alignment, actually partial level alignment. This is why compounds are very flexible, have different scaffolds, like small combination. If you need to generate conformance with multiple issue vectors, you should have this roll-up segregation.
Yeah.
Something like orders of magnitude.
Yeah, but it's actually not very technical comparison is very different.
Yeah.
Yeah, but this is just a ligand-based technique. So like within the spectrum of ligand-based techniques, that's like expensive. That's expensive. Like flexible alignment is expensive. But honestly, designing a pharmacophore ligand usually people don't. Yeah, for example. If you have like a little bit
But
like
it's kind of you just change.
just a simplification due to inability to include all this variety of possible representations of a molecule in our statistical model. But even these representations, they are still not complete, because molecules are not molecular graphs. Molecules actually are 3D creatures, and they exist in 3D space. So they have shape, volume, and other 3D characteristics, which is also important for biological activity and for the recognition of a protein of our receptor. And okay, we can generate a single conformer for a molecule, and again, we can calculate some feature vector and build a QSAR model based on this. This is a classical 3D QSAR pipeline. And even this representation is still not complete, because molecule does not exist in a single conformational state, usually. Yeah, benzene, for example, has a single conformer. But the majority of molecules have more number of conformers than one. And they actually exist in multiple conformers which are exist in equilibrium, and only some of those conformers are relevant for biological response. Only some of those conformers can really bind to our target. And in this case, we have a real issue. Okay, if we have multiple instances of a single molecule, we have multiple feature vectors which we calculate from every instance, in this case conformers. How we can manage this within statistical modeling? The classical approaches, they were developed many years ago. They named 4D QSAR. They try to address this in a way to simplify the problem. Goes from 4D to 3D. This is a classical example of the work of Rotfinger, who was the first one who suggested this approach. It's based on the 3D representation. So again, we generate number of conformers for molecules in our data set. Then we choose a trial alignment, align all conformers of all molecules based on this trial alignment, based on the pharmacophore, three-point pharmacophore features. Then they calculate average occupancy in the grid, so the molecule, all aligned molecules put into the grid, and they calculate average occupancy for individual molecules by their conformers of a particular grid cell. And then they use this information to build a model, and here is a trick that they calculate, they average the average representation of all conformers in a single value for every cell. So it's just the average occupancy. So this is something like an average descriptor value, because for single conformers, the descriptor value would be 0 or 1, for example, whether this cell is occupied by a particular atom or not occupied, for individual conformers. This approach received some attention. It was applied for many years, and they developed by different groups. Even I was participating when I was in the beginning during my PhD study. I also participated, contributed to this field. Here is just another example, more, I would say, modern, more recent one. Also, researchers just try to compare different types of representations and modeling. So they use 2D, 3D descriptors, and 4D descriptors obtained from the MD simulations, trajectories. So they perform MD simulations, retrieve the conformers, 15,000 conformers. For every conformer, they calculate 3D descriptors. And again, they made a trick. So they average the feature vectors of individual conformers across the whole set of conformers for each molecule separately. Additionally, they calculate not only average, but also standard deviation of those values, and they can concatenate these two output feature vectors in a one vector. And they use this to model. And what they found that using 2D representations was quite didn't change a lot the accuracy of the model. Even addition of these 4D descriptors obtained from multiple conformers also didn't improve substantially the model. Yeah, it made some contribution. But when they use this 4D representation alone, they received quite moderate accurate models. So this means that the contribution of individual those 4D representation is not that high in this case, and generally this QSAR currently is not that popular due to such issues. And what I would like to highlight is that in all existing approaches currently available, the trick here, why we can use them and why we can apply currently existing learning algorithms, is that when we calculate the feature vectors for individual instances, we calculate some average or somehow aggregate them to create a single feature vector to be applicable to classical machine learning models. Here, for those of you who are interested in 4D QSAR, here is a good review which overviews the last 20 years of development of 4D QSAR. But again, all of them use the same scheme. Yeah, in some of those approaches, researchers try to not simple average conformize, but they try to average based on the Boltzmann distribution. So this was a weighted average. But again, it is a big question how to calculate this Boltzmann distribution, because usually everybody calculates it in vacuum, which might be quite different from the situation in the water medium with particular ions and so on. So that's why this representation can also not perfect, and it's also something like artificial contribution to this. To address this kind of issues, an approach named multi-instance learning was suggested almost the same date when 4D QSAR was developed by Thomas Dietrich, and this approach was suggested explicitly to solve chemical problems and explicitly to solve the task when we have multiple conformers. The idea here is that, okay, we have multiple conformers for each compound. Here you can see these circles and these shapes inside these circles. So the circle is a single molecule and these shapes are conformers. For inactive compounds, those red ones, all instances for all conformers are considered inactive. For active compounds, at least one conformer should be considered as active. Of course, if we properly sample the conformational space, but we assume that we can do this. And the goal will be not to separate those actives from inactives, but individually, but separate them based on these instances. So we have to just separate instances of positive class, not all instances of active molecules from inactive ones. which were already published on this topic. So we try to somehow revisit this on more modern level because new neural networks gives a lot of flexibility and possibilities to handle this complexity. Here is the scheme which I showed you before of the classical 4D QSAR representation when we just average the descriptor and make a model. And this scheme is identical to the back wrapper in multi-instance learning algorithms. So we average information about individual instances, in this case confirmations. There are also another kind of approach, instance wrapper. So in this case we consider each instance as individual training example, and we assign the same activity value as for a whole molecule to each of these confirm. In this case we multiply the number of rows in our data set, and we use the whole data set to make a model using the, again, classical algorithms, and then to calculate the final value, we average the predictions of individual instances. Quite simple and very fast. With introduction of those new neural networks, we can do more complex stuff. So we can, for example, use these feature vectors, input feature vectors, like classical descriptors, and pass them through layers of neural network to create embeddings, which may be more better fine-tuned and better adjust to solve a particular task. And then we can also average these embeddings, and we form the finding the correlation with endpoint value, like in a classical machine learning algorithm. So this is a back-net approach, which is quite similar to back wrapper, but it just additionally convert feature vectors to embeddings. Instance map is another analog of instance wrapper. Again, we create the embeddings from the input feature vectors and then use individual instances as individual training examples. We perform prediction and we average the predictions for individual instances. But in all these schemes, when we use averaging, we do not consider the contribution of individual instances to the model. And it's quite obvious that not all instances are equally important for final prediction, for final accuracy. That's why more complex architecture was suggested. So we again take feature vector, create the embeddings, but then we do not simply average those embeddings, but we use the so-called attention network, which assign weights for individual instances, and then we calculate weighted average. And then we again build a classical QSAR model, or in this case, just a few dense layers of neural network to find the final value. And the additional output of this algorithm, which would be quite interesting and important, is interpretation and ability to identify key instance. Because we can analyze those weights and we can find the most relevant instance, most contributing instance. And in this way, we should be able to identify biologically relevant conformer, which, from the point of view of a QSAR model, is responsible for the endpoint value and for recognition of our receptor. We validated this approach quite interesting for us. We still do not have an explanation why it worked so well. But yes, all other multi-instance approaches were comparable to each other in accuracy, while this instance wrapper really performed very well. Then we compared this instance wrapper with other 2D approaches, classical approaches based on the Morgan fingerprint or alternatively this ECFP fingerprint which we represented, and physicochemical or 2D pharmacophore fingerprints. And in all those cases, average accuracy across multiple models was the highest for multi-instance wrapper, finally, based on 3D pharmacophore representation. Interestingly, that back attention network is the most advanced architecture at that time, was comparable to Morgan 2D Morgan fingerprint approach, and you can see here in the rank, so the difference is not statistically significant because between those two approaches, and again, instance wrapper performed quite well. And those reference 2D models were outperformed. And what is the most interesting and quite important to know that for reference we also use the single instances, so we choose most energetically favorable conformers and build classical 3D QSAR models based on the single conformer, and we found that those models were mostly not predicted at all. So they have almost always zero correlation coefficient for test set, and it ranked at the lowest rate. This just demonstrates that considering just one conformer, it's not enough to get a good prediction. Yeah, it may work if your molecules are rigid, but if they are flexible, it's really tricky to choose a proper conformer for such a model. Here is just the comparison between those 2D Morgan fingerprint model and 3D multi-instance wrapper, just to show you how different the accuracy was for different models for the same data sets. So lots of data sets, and you can see that, for example, for this data set, the Morgan fingerprint didn't predict nothing reasonable, while for multi-instance learning we obtained quite high value for R square, and this model is highly predictive. So this is another way to represent here 2D, and here is multi-instance learning, and in many cases we have improvement over 2D models in many of those cases. And we try to somehow rationalize and understand why it happens. We try to find some recommendation in which cases we can apply multi-instance learning, in which cases it's not reasonable. We analyze different type of physicochemical parameters of those molecules of those data sets, but unfortunately we found that the difference was not statistically significant in many cases between those groups which are well predicted by 2D models or better predicted by multi-instance learning models. So that's why it's difficult currently to say, okay, which type of model will be better on a particular data set. So it is just empirical knowledge. From a practical point of view, since 3D and multi-instance learning approach is more computationally demanding because we need to generate a lot of conformers, it's better to start always from the simple model, like 2D model, and then if it fails, go to the higher level of representation. But 3D QSAR is not reasonable to use, and in this case, 4D QSAR may be better to apply after 2D model. And we also try to address the question regarding the identification of biologically relevant conformers based on this attention network architecture.
You are muted all the time.
Super.
So, 3 rounds of the beginning.
have a time machine to return back, unfortunately. Sorry. Yeah, so we tried to address and evaluate the question about the identification of biologically relevant conformers. For this, we, from the same sets, we looked in the PDB of, for crystal structure of molecules. These are 4 endpoints. Crystal structure of molecules which were not in the training set. And we use them as a reference examples. We predicted for them endpoint values and retrieved the most contributed conformer for each of these compounds and compare with different reference approaches. So the last bar, this dark orange, it demonstrates the number of molecules which will be identified if we used just random choice. So if we randomly choose a conformer, and whether this conformer will be within 2 angstroms from the crystal structure. And in many cases, you can see that it is pretty successful. So it's more than 50% of cases that randomly choosing the conformer, we can get quite close conformation to the X-ray structure. And this means that RDKit does its job pretty well already. And can we improve this? We compared these outputs to docking, this dark blue, for example, and docking could identify the relevant poses comparable to the random choice. So it's also more than 50% in many cases, but comparable to RDKit. So is it necessary? It's a question. Also, we receive the same output if we use lowest energy conformer. So just selecting a lower energy conformer receive the same, almost the same output, so comparable to the random choice. This first bar is the total number of structures in each data set. And if we use multi-instance learning, we observed some improvement. Yeah, its improvement was not that much. In these cases, it was also worked like random choice. In some cases, this improvement, we observe some improvement. So again, it's not, how to say, very encouraging outputs, but it just demonstrates that, yeah, these models in some cases can improve the ability to identify relevant conformers. And this is maybe the biggest question for today for us as researchers, to answer this question whether we can really predict and retrieve these biologically relevant conformers or not. It is still unexplored issue. Here I just want to show you some previous approaches because previously neural networks were not used for this kind of tasks. So just to let you know, for example, citation KNN, it was quite popular at that time. So it computes the Hausdorff distance between 2 bags, and in this way it compared the similarity between 2 groups of instances. And Hausdorff distance is the greatest of all the distances from a point in one set to the point in the other set. So this dashed line is the closest distance of this point to these molecules in the back 2. This dashed line, for example, that this is the closest distance from this molecule to all points here. And this is what is the Hausdorff distance between these 2 sets. This is how to calculate the similarity between 2 sets of points. Another approach is a diversity density. Here is instances of individual bags, molecules, whatever. This green one are positive, this red one is negative bag, and this algorithm tries to find the point where mostly populated by instances of positive bags. And then to make a prediction, it just calculates the distance from this diversity density point to the closest instance of our test set example. They are quite simple, obvious, but they're not so accurate as modern approaches. However, the complexity and ability to represent a molecule or our object is not limited to polymorphism type of ambiguity. It can be also described part to whole, where instances could be, for example, atoms or group of atoms. That's also possible. And it's quite popular in bioinformatics that we can use subsequences to represent the whole sequence. And this also can be modeled using the multi-instance learning approach. I will show you just a few examples. Here is a paper which I discovered very recently. It was published in 2023, but for some reason I missed it. And it's quite interesting approach where they used as instances metabolites. The modeling task was to predict the mutagenicity of compounds. It's a well-known Ames test, which is used for compounds and which returns you the qualitative output, whether your compound is mutagenic or not mutagenic, and you can build a classification model. And those models are quite important, and they're used by regulatory bodies to make a decision about the potential hazard of different chemicals. Here is DEREC, LSMA, and other standard or commercial tools which are used for prediction of mutagenicity of compounds. And all of them use just a single representation of a molecule, for example, this one. These researchers suggested that, okay, we can represent this molecule by explicitly enumerating or predicting possible products of metabolism by cytochrome. And in this case, they represent the molecule not as initial, not only as initial molecular graph, but all other entities which are predicted to be possible to be metabolites. And in this case, they consider that, okay, all metabolites of non-toxic compound should be non-toxic, and at least some metabolites or the initial entity in the toxic compound should be toxic. And they built SVM models based on this representation using a specific algorithm for multi-instance learning, and they discovered, yeah, in the whole, in general, the accuracy of the model didn't change, but for particular class of compounds, they observed some improvement. For example, for nitroaromatic, they demonstrated that they could improve overall accuracy, balanced accuracy in comparison to commercial software. But yeah, it's maybe not the great improvement, but in some cases it can improve it. It's just a good example to demonstrate that when we consider instances, we shouldn't be tightly connected to conformers or some particular type of representation. This could be a metabolite. It's really quite smart way how to represent our molecules. So we provide explicitly information about potentially useful metabolites which can be captured by the model. Another example is atoms as instances. I will not go into very much details regarding the graph convolution neural networks. I will just briefly explain you how it performs this modeling stuff, because it is quite popular currently and widely used. It achieves quite high accuracy. So we use a molecular graph. Each atom is represented as a feature vector, which includes, for example, charge, atomic number, some number of hydrogens connected, and some other characteristics of atoms. Then those features of each atom pass it through the neural network to create embeddings of each atom. Then those embeddings for the atom and its connected neighbors are somehow aggregated. For example, can be summarized, and then apply some nonlinear function transformation. And in this And further, we can just perform pooling, so we recalculate features for each atom. So for this initial central atom, we aggregate in some way the features of connected neighbors in these two steps with pooling. And this procedure is repeated several times, and you grab the information in each atom about more and more distant environments. So if you perform 2 rounds of this training, we get information about atoms at a distance up to 2 bonds from the central atom. It's very similar to what Wim showed about these ECFP fingerprints. And finally, when we got these feature vectors for every atom, they simply average across all atoms to get a one feature vector for a molecule. And this strategy, it's not recognized in the community, in chemoinformatics community, but it is identical to multi-instance learning paradigm. So they calculate this feature vector for individual instances, which are atoms in this case, and then just average them to get a single feature vector, which is used to create a QSAR model. And this type of model was used to build a model to predict pKa values, micro and macro pKa values. And the idea was that they originally predict micro pKa values, so pKa values for particular atoms. And then, using these equations, they transform these predictions into the macro pKa values. And this is a nice example of application of this algorithm, and this was the first probably recognition that graph convolution is internally a multi-instance learning approach. Here are just examples from this model, so they perform really well in comparison to standard approaches using the 2D classical 2D representations, and they could perform pretty well and predict the most acidic and most relevant center in many cases, but not in all of them, because for some cases it was quite difficult to decide, and majority of those cases belong to those oximes. So it's very difficult to decide whether which center is truly will be deprotonated. Those nitrogen or those oxygen. Even for human experts, it's a difficult question, and they're very, very close. So the model, yeah, made some errors, but it made errors in these, I would say, not fully clear cases, even for human experts. Another example is from peptide sequences as instances. In our body, we have this major histocompatibility complex class 2 molecules which work in our immune system. When we have some external exogenous peptide or protein, the cell consume it, then enzymes cut this protein into pieces from 11 to 30 residues number. Then those pieces of proteins, those peptides, are bound to this complex, because it has a large groove which can adopt quite large peptides, and then this peptide present this complex presents these peptides to the surface of a cell to react to cause the further response in our immune system. So immune system can recognize those short peptides as dangerous and then can produce a corresponding response. And when we model the potential hazard of different peptides, it's quite important feature, especially for vaccine development, because vaccine can also trigger this immune response, which is undesired. in some way. It can also produce too high, for example, immune response and so on. So that's why it's good to predict possibility of an immune response for proteins, but we cannot use the whole sequence for modeling and for prediction. That's why researchers suggested to just cut this sequence with a sliding window on subsequences of lengths from 9 to 11, for example, because it was demonstrated from experiments that this length is really responsible for recognition. So it's not necessary to be the whole length of up to 30 residues. And then you can represent your protein as a set or bag of short peptide sequences, and only few of these sequences are really responsible for binding with this complex and trigger the response. And they were quite successful. I didn't provide the reference, sorry for that, for the paper. They were quite successful in modeling, and it is quite useful technique. It's quite widely used in bioinformatics. And this is just another example of what can be an instance. So it's not only conformers and atoms. Okay, I will skip this example since we are almost out of time. Here are just a few our publications. If you are interested in this approach, you can start learning from reading this review or some papers which we published on this topic regarding the biological prediction or prediction of selectivity of chemical reactions. Here is a list of available tools. Unfortunately, currently there are no, I would say, convenient tools which can be used to solve chemical problems, which can be natively applied to it. However, there are a lot of tools developed in Evolve. Currently, we develop our tools here. The last one is also developed by us, but we want to improve it and completely revise, so currently we are working on it. So maybe this year it will be finished, this work, and it will be more easily available for end users, for cheminformatics community, to use this kind of models. And just at the end, a few conclusions that this multi-instance learning model can really improve the accuracy of your models, but they're more time-consuming. So, as I told previously, it's better to build 2D models than go to more complex level. But it can really improve the predicted activity and accuracy. It's also possible to identify biologically relevant conformers, but it is still underexplored tissue, and this is like one of the major future direction of research, I would say, in this field. What is also important is that, from my point of view, it should change the paradigm of how we think about molecules. So molecules are not just a graph which we can draw with the Marvin or other tools. Molecules are more complex, and you can consider them as a set of atoms, set of conformers, set of tautomers, protomers, even those metabolites, whatever. So just widen your perception of a molecule. And another future direction of research would also be interested is to test how different 3D representation will address and do they have some impact, which impact they have, which representations are stably working better than others. That's also an unanswered question. So in this field, there are a lot of white spots. So if you want to contribute, you can choose any kind of topic and it will be unexplored, or almost unexplored. And at the end, I would like to acknowledge the contributors. So this work formed with Professor Warnek, in collaboration with Professor Warnek, his former PhD student, who was my main developer of these tools. These were my students and postdocs, Timur Majidov, who moved to UK, and some other colleagues from other institutions and companies. So thank you for your attention. And if you have questions, I would like to ask it. So we are almost out of time, but we have time for 1-2 questions.
can take both questions if you want.
No, just one.
Yeah, just one. Okay, so sometimes when you have inside of your bag, the relative prevalence of the species in there can very strongly differ. For example, let's say when you have metabolites, some metabolites will be likely metabolites, some of them will be minor, or in practice they will actually not be detected. So are there some ways to cope with that?
This is another major complexity of these multi-instance approaches and 4D approaches as a whole. This is the same question as when we generate a lot of conformers, not all of them are relevant for biological response. And this creates a complexity for a model to choose a proper conformer. So currently I would say that those approaches which are available, they may identify something relevant, but not always. But they can identify something similar to relevant. And maybe this is enough. But yeah, you can really overfit your model in this case. If you supply a lot of unrelevant information, it can fool it. So this is a trade-off. It's still unexplored again. So it may affect. Yeah, Martin?
Yeah, so thanks for the great and inspiring talk, by the way. So my question was, in your experiments, you focused on regression models. Do you think it would be worth it to also look at classification tasks?
Yeah, in our cases, yes, we used mainly regressions. We tried to apply this for classifications, and it was quite interesting for us that we didn't see much advantages over 2D approaches already for classification tasks. But again, we didn't dive deeper on this question, so it's also still to be explored to answer the question whether we maybe made some errors, mistakes in our modeling pipeline, or it's real response. But for classification, currently, we cannot say that it will work better than classical approaches. Yeah.
If you can go to your slide number 5.
Sure.
I have just some wild idea. So you are plotting prediction versus experimental. What if you plot prediction versus prediction from different models? Will it give any mess, or maybe we'll get some pattern?
It's not our work, so researchers didn't do that, but usually they can be correlated. They should be correlated. Maybe less than with experimental values. But regarding those 4D, yeah, it could be a good just to find the correlation. But since
there may be something which you could see then why some work, some doesn't.
Previously, again, from previous experience of mine when I worked in this field, how to say, more intensively, yeah, we performed this comparison, and usually we observed that individual predictions across different models are usually correlate with each other, but not that good as an endpoint value. But when we combine them together, this may have a consensus effect, so they cancel error of each other, and then they can improve the prediction, for example. So yeah, they can, when we concatenate descriptors, we can also add some additional information for models. Okay, so thanks for your attention. We can make a short break for 10 minutes before the next lecture will start. So thanks.
Crazy. Yeah, you hook it over your ears and you make sure it's unmuted. Yeah, there's a little switch here. And then is it on or off?
All right. So.
Now you are being recorded.
Oh, does it work? Oh, that's nice. Perfect. And does it have a... How do you do the laser thingy? Oh, like this. Oh, that's perfect. Then I don't have to stand there. That's nice. Yeah, I think this is nice. Yeah. Yeah. Okay. So yeah, I hope this is on. So.
Others want to drink more coffee.
Okay. So should I start or should we wait?
It's up to you, but you have 1 hour.
I would count 2 minutes.
I will wait. That's fine. It's true that there's lunch, but I don't want to keep people from eating. It's always risky to have the lecture before lunch. You see angry looks, you know, like hungry people. That's true. Yeah.
Missing people? Just few of them are there.
Okay. But there's still people trickling in, so yeah. Maybe I'll give it 1 more minute.
Shall I close it?
Yeah. Maybe. Yeah. We were 5 minutes late, so I think I can wait 5 minutes. That's fine.
They will go later for lunch.
Yeah. But it's okay. Like there are things that I can skip, so I don't know how long it will actually take, so that's going to be a bit of a surprise. Yep. All right. So yeah, hello everyone. It's nice to be here in Olomouc as a speaker this time. I remember my last time at this conference was many years ago. Maybe it was like the 2nd edition when I was actually starting my PhD. So it's really nice to actually come back and do a talk for a change. So I'm Martin. I'm from UCT Prague, VŠHT. But right now I still have a double affiliation with University of Leiden in the Netherlands. In particular LACDR, which is Leiden Academic Center for Drug Research. My focus of research is mainly QSAR, but also more lately de novo drug design. So those are 2 main aspects that I like about cheminformatics. But today I will focus mainly on de novo drug design, and first I will show you a little bit about the methods in general and what de novo drug design is, a bit of history. Here's just a picture about what phases of the drug discovery process we can use de novo drug design on. So mainly I would say lead identification is the main phase where you can use de novo drug design, but you can also use it for lead optimization to maybe automatically generate some hypotheses for how to improve different properties. So you can use QSAR and toxicity prediction to basically guide lead optimization, or you can use it as a replacement for virtual screening in these 2 phases. Okay, maybe I'm too far. Oh, okay. Yeah, so like I said, in lead identification, it circumvents the need to do exhaustive sampling of large chemical spaces. And in lead optimization, you can use multi-objective optimization to score the generated molecules and basically explore only a small spot in the chemical space. I borrowed this from Johannes, because this was a really nice slide. So usually what people say is the main reason to use de novo drug design is that the theoretical space of drug-like molecules is really huge, and you cannot explore it exhaustively. So that's why I included it here, but I think maybe another reason also is that the diversity of these make-on-demand libraries that we like to use from Enamin, for example, is quite small. So because it's based on maybe a few building blocks and only some chemical reactions, then the diversity of these libraries is actually not that large, and you're not able to maybe access some more bespoke chemistry that usually leads to successful drug candidates. So I think that's also one reason to maybe use de novo drug design, to get some more out there ideas into your process. So de novo drug design actually is quite a new, like in comparison to QSAR, it's quite a new field actually. But already in 1993, we can see this paper by Murko and Rothstein. They were trying to do something like we're already trying to do, basically find some way to combine some fragments of molecules to fill a binding pocket. But these kinds of experiments, they were really only possible with the help of computers. So that's basically where people started to think actually about de novo drug design, and that's where it all began. And when we look at how such papers look today, yeah, of course, you have better graphics. And there's usually like this block of AI that people just stamp on everything. So yeah, the methods, they have changed. We're trying different things, but basically we're still trying to achieve the same. So today we're going to look at maybe the more contemporary examples, but we will also be looking a little bit back and trying to see where the field goes. So yeah, and this is me just like trying to figure all this out. So hopefully you can do it with me. So I think a nice way to look at this is also through this kind of scheme where you look at what kind of data you have available in your project. So I try to put a lot of citations in my slides, so if you can't read them, that's fine, you can take a look at them later. So probably the best case is where you have a structure and you have some bioactivity data for a series of compounds, ideally a diverse set of compounds. So what you do then is the approach that basically goes back to 1993. You can use some fragment-based or atom-based generation in the binding pocket to find basically new ligands with a conformation that can actually fill the pocket and make some good interactions for favorable binding-free energy, which is the objective you kind of want to optimize there. But you can also use actually 2D ligand-based generation with some 3D structure scoring. So for example, you can create a 2D graph with some genetic algorithm or by combining fragments again, and then you can try to use docking or some other 3D approach to sort of relate how well the structure will bind. And actually there's a really nice blog post about this, which I suggest that you check out, where it's shown that actually sometimes these 2D based approaches with some 3D implicit information are better than actually doing the generation in the pocket itself. So another scenario is maybe there's no information about ligands, but you have the protein. So again, you can use fragment-based and atom-based generation. It's just not going to be informed in any way based on known ligands because you don't have that information. But you can still use the same method. Maybe you just use some building blocks that you can combine with some combinatorial reaction, something like that. But there's also like some approaches that use modern deep learning methods like stable diffusion to basically just gem a ligand up in the binding pocket. But these have a lot of problems still, but it's quite an interesting prospect. And there's one example of such method here that I wouldn't say will perform very well for you, but it's a start. So then we move to the case where actually we have some information about the ligands, but no information on the protein, or at least on the structure. So in that case, again, we can use 2D and 3D ligand-based generation with some kind of scoring. So yeah, you cannot base it on the protein itself, but you can use QSAR modeling since you have the bioactivity data. You can maybe build some pharmacophore model based on some common features of your ligands, or you can use shape similarity. You can score the ligands based on how similar they are to good molecules in your data set. You can generate 3D conformations for them. You can perform some shape matching, things like that. And maybe there's a few more that you can dream of. So that's something you can use here. And then, of course, there's also the option where you don't have any ligands to really start with. You also don't know the target. So that's quite a difficult situation to be in. Surprisingly, there are still some options that are being explored. We actually looked at one recently in this paper, where basically you can still use, if you at least know the protein that you're targeting, you can use a sequence and using a multi-model kind of like a PCM generative approach with deep learning to generate some molecules with a model that has some information about maybe related proteins that have similar sequence, and it can still suggest some ligands based on what ligands bind to the similar proteins. So maybe that's something you can use for some like orphaned targets. And then of course, I would even say that if you do some combinatorial library design to actually do virtual screening on, you're already doing some kind of de novo drug design. So that's already also, I would say, falls under this this hood. But then it's of course quite an expensive approach to select what you want to screen. So now I'm going to take you on the tour of some of these methods that I outlined here. So I will start with the in-pocket 3D generation. How to do it? There are a few examples. So you saw the paper from 1993. So there are various methods that you can use for this. Some employ genetic algorithms and heuristics to combine fragments to grow them with atom-based modifications to fit maybe some more narrow crevices. So there's a lot of ways of doing that. So this is more traditional. I would say this is an obvious and transparent solution to the problem, basically to find some structures that bind using some guided search. But more and more lately people are trying to use generative deep learning to basically do the same and do the prioritization of these, of how these fragments should be combined and grown. Example is, for example, this frame method when you have an AI model that determines rather than some heuristic. Or basically the AI model is in the place of the heuristic here. And I also included this example on like chemical space docking when they use the concept of syntons, where basically these are fragments that can be combined like a Lego with other fragments with simple chemical reactions. So then also the ligands that you generate in the pocket, they are already synthesizable and chemically relevant, which often is the issue with generated molecules. So yeah, there are some downsides, mainly with the deep learning models. You don't really know their limitations because it's really hard to see inside the model how it decides which fragment to combine or which fragment to generate. So it's really hard to then make some optimization if it doesn't work. So that's yeah, some overview of this. Then I was mentioning 2D graph generation. I would say that's the most explored and abundant set of methods in this area. So again, you have some fragment growing or joining in 2D. So there's maybe like two, I would say, most prominent examples. So GraphGA and CREM that we will also see today at the tutorial. So basically all you can do in 3D, you can also do in 2D. And it's easier to do it in 2D. So that's why people use it the most. But more recently, again, generative deep learning has really flourished in de novo drug design. So you have all these different architectures. You have RNNs, VAEs, GANs, not these. You have normalizing flow models, transformers, and maybe probably some other architectures that I haven't mentioned. And a popular framework to use for training of these models is reinforcement learning. So I will have a segment on that as well. That's basically a way of integrating an objective function into this 2D generation. So you can also, it's a way to facilitate this implicit 3D information via docking, for example. So people have explored that as well. So let's dive into some of these architectures. So recurrent neural networks, I would say probably most prominent and most successful example, especially due to the reinvent software, which is what researchers in the public domain mostly use when they do experiments with different strategies or even when they're doing applications. So a little bit about how that works. So in a recurrent neural network, basically you start with some kind of data set of molecules. This can be Campbell or it can be zinc. And then you're trying to teach your model to basically reconstruct new molecules that look similar to this data set. Basically, that approximates the distribution of the chemical, of the known chemical space. And you can do this by basically splitting each molecule. So you can represent the molecules as smiles that you can break down into some tokens. So smiles consists of letters like this. So we represent different aspects of the smile string with different tokens. So you can split the molecules' smile strings into tokens like this. And then basically the RNN is trying to solve a classification problem where you start with a Go token, which means now we're starting to generate a smile string. Then it goes through the neural network, which has specialized layers consisting of either GRU or LSTM cells. LSTMs are the more preferred options these days. And then at the end, so initialized with the Go token, it tries to predict the next token. So in this case, this nitrogen here. So first you randomly initialize this network, so it will just associate a random letter here from the vocabulary. So we know nitrogen is correct, but the network doesn't know it. So if it generates something else, then we say how correct it actually was for this particular smile string. So then we can use simple negative log likelihood loss function to do then backpropagation through the network, do gradient descent and all the stuff that maybe you know already, to basically adjust the weights so that what the network generates here is closer to nitrogen or closer to what we expect. And that's basically one pass through the network, but you can do multiple recursive passes actually, so that's why it's called recurrent, because the architecture allows that. So once you generate one token, you can generate another one based on the tokens before. So the network, these cells, they're called long-term, short-term memory cells. It remembers the preceding tokens, so that's why these architectures are also used in analysis of time series data, because they can remember what was before, and then you can use that information to actually generate other tokens. So then you can generate a smile string like this, and by training you can teach the network what are the kind of smile strings that you want to see, and in the end it will be an approximation of the chemical space that you started with. So that's a very basic architecture that's commonly used. In the natural language processing domain, these guys were already surpassed by transformers. but I would say in de novo drug design, they're still quite prevalent and people use them a lot, even though there are plenty of studies using transformers, including one that we published as well. So that's one architecture. Then we have variational autoencoders, VAEs, which sort of builds on this. So for this encoder, for example, you can have an RNN architecture as well. And the idea there is that basically, instead of doing the pass like I showed on the previous slide, you insert something called latent space in the middle. So then you encode the molecules, you basically compress the information of this space into some n-dimensional continuous space. And that's both the blessing and the curse of this method, actually. So chemical space is not really continuous, so it's not really an accurate representation. But what it allows you to do in this latent space is basically to use some kind of optimization. Often people use Bayesian optimization to move continuously in this space, so explore different areas, and then you can use the decoder to decode back into the smiles. So what this allows you to do to basically have some kind of objective optimization included, because you first train the model, you create this latent representation of the chemical space that you're training on, and then you can explore this latent space and try to decode molecules from this latent space that actually have some beneficial properties. So you can try to use maybe a QSAR model, you can use this as descriptors, and then you can go back and you can try to look at what part of the space actually generate the more active molecules. So that's one thing that you can do with this architecture. The problem is actually here, because this is continuous, you cannot always actually find an equivalent molecule for some combination of these latent descriptors. So another really nice architecture, quite interesting, is generative adversarial networks. I actually don't see them used that much these days, but they're still there. And again, it's more of like a learning framework. So you have some generative network module, again, can be an RNN, in the step one. And it's, first you add some random noise in the beginning. It generates some molecules, maybe not even possible molecules at all. So then you use a discriminative network. So this, you can see this as an adversary trying to like feed this discriminative network some fake instances and trying to fool it. But we actually helped the discriminative network here with real instances, and it's taught to actually discriminate between fake and real. So it can then give feedback to the generative network if it was able to say yes or no, this is fake, this is real. And then the network can actually adjust its parameters so that this discriminative network can no longer distinguish between fake and real instances. So then that means this generative network is trained, and it represents, again, some part of chemical space that we're interested in. And again, there are strategies to basically combine it with different objectives, different architectures, use also reinforcement learning to do both this third step and also include some objectives. So that's something people have been exploring as well. So I talked about reinforcement learning already. So here's a little bit about how it works conceptually. So in reinforcement learning, you have this concept of policy, actions, agent, environment, and reward. So you basically have your agent, which is an AI in this case, and you're trying to explore some environment by basically adjusting the state of the agent in this environment by giving it actions to do. So you can, for example, program an AI that can solve some kind of a maze, and based on how quickly it solved the maze, what kind of actions actually led to the solutions, you can give it rewards in the end. And then you can adjust the weights of the agent again, and do this iteratively until it actually is able to find the best solution using just this state and action space. So here's an example, very easy to grasp on teaching AI to drive. So this is a simulation of a self-driving car. Here, the action space actually is just turn left, turn right, gas on, brake, things like that, simple actions like this. And then we use reinforcement learning, basically randomly probing the AI and telling it like, okay, now you did well, now you did wrong, and eventually it learns how to complete the course. What's actually interesting about this GIF, so it comes from this website, which I highly recommend, is that it shows the concept of overtraining in these models. So Wim was talking about overtraining. So these models, they can also overtrain. So in this case, the way or the success of the AI, you can see that the white car is actually not so good at completing the course as fast as the yellow car. And that's because the yellow car always started from one position. But if you change the position, the initial state, for the model, and it's only taught on like starting here, it can complete the course, but it will make some mistakes. So that's basically how you can see it overtrained. It's not able to like 100% generalize, but sort of it can. So that's also what we actually see in these models, that they can overtrain, and sometimes they if you feed them some of the models, they can actually take some information on the initial state. For example, we can give a substructure that we want to generate from. Then they can generate something that doesn't make really any sense, like this, like making such a random turn doesn't make sense. So sometimes they generate something that doesn't make sense, but sometimes this is also, they can generate maybe some substructure that could be interesting or creative or something that maybe we wouldn't think to explore yet. If it's a signal or if it's just random noise, that's up to interpretation. So this is again how we do this in de novo drug design. So it's very popular for a multi-objective optimization. There's a concept of policy gradient. So if we imagine this prior model is this RNN network, for example, and this is also the architecture that we will be working on in the tutorial in the afternoon. It again works like this. So model generates, defines this agent model, it generates some smiles. We have a scoring function like a QSAR model or synthetic accessibility model above. It gives a reward. We adjust the agent weights to generate better smiles that satisfy the scoring function, and we iterate until it can get no longer any better. And how to integrate this in a neural network is exactly with this policy gradient. So this is a loss function that you use to calculate the gradient descent, basically. So the log likelihood I already mentioned is basically kind of the distribution of the input chemical space. So that's what you ideally maybe you want to bias towards, but it can also be a general space. It doesn't matter. So you can still keep the model grounded using this. There's no problem actually using just the reward, but this is just an example to make some connection to the previous slide. And then you have this reward parameter where you basically adjust the loss based on how bad the molecules are. So the worse the model does on the objectives, then the more we need to adjust the weights. So then this framework actually allows you to get away from your prior chemical space and explore new options. And the rate of this exploration is defined exactly by the reward, but you can also do other strategies like we do in DrugX, which we will play with a little bit in the afternoon, so I'll leave that. Yeah, so this is what results in the policy gradient. So this is how maybe on the inside you can imagine this, this works. The problem with reinforcement learning in general is very stochastic. It can easily lead to unstable training, depends on hyperparameters, your architecture. So it's very finicky. And yeah, how to parameterize it on different data sets, you will get different success with different objective functions. So it's quite tricky. But when it works, yeah, it works quite reasonably well, and you can get some interesting insights. So yeah, that's basically kind of concludes sort of the general introduction of my talk. I think the timing is right. When do we?
Half an hour.
Still I have half an hour, perfect. So this is basically my focus of the last 3 years that I've been doing. Basically trying to put molecular generation into practice. So the important stuff is basically how to use maybe AI or some traditional like reaction enumeration approaches to get to a set of virtual compounds that we can actually select good candidates from and actually do synthesis and experimentals and biological validation that we actually designed a good ligand that we can make that somewhat works on our target. And this is what people don't usually do because it's very costly. It requires usually collaboration with medicinal chemists. So a lot of these generative papers that you will see, they actually don't validate experimentally that often. They just look at some parameters of the generated space and they compare to other methods, how diverse it is and things like that. But I think it's really important to actually put these approaches to the test and do this. And of course, I was not the only one doing all that. And there's a lot of people behind a lot of the studies that we have done. And these are just some examples. We're developing different kinds of software. So there's this DrugX molecular generation algorithm that we will play with in the afternoon. There's synthetic accessibility scoring, which I will talk a little bit about after this. Then we have, for QSAR modeling, we also have a framework which is easy to actually integrate across all of these packages. And now we're also developing this Spock molecular docking SBDD package that's a bit similar to what Pavel was showing yesterday at the tutorial with EasyDoc, but here we're focusing a bit more on actually interoperability with all these other packages and maybe machine learning aspects using graph neural networks as well. And then we also have this graphical user interface, which maybe I will showcase in the tutorial. We will see how we do on time. In this study, we actually had a target called monoglyceride lipase. It's an interesting target because it's an enzyme, but it affects cannabinoid receptors. So if you can knock out this enzyme, you can actually modulate activation of cannabinoid receptors in the brain. And this is how DrugX works. So you already know what reinforcement learning is. So this loop is kind of obvious. DrugX generates some compounds. We have some scoring environment. And then we're using actually Pareto optimization. I'll explain at the tutorial to optimize multiple objectives. So in this case, 2. One objective is synthetic accessibility, because that's really important to keep the model grounded in what we can do. In this case, we actually used a trained machine learned score that can predict if we can make the compounds in-house or if not. So that was really useful to us. And the second objective is just a traditional QSAR classification model in this case. By the way, in my experience, classification models work a little bit better in reinforcement learning than regression models. That's actually quite interesting, but nobody knows really why. Or at least I don't. So that's still under investigation. And the way DrugX works, this is a bit of a segue to the tutorial later. You actually have 2 networks. So you have an agent. So that's the agent from the reinforcement learning terminology. So that's actually the network that's being trained. But then you also have some fine-tuned prior network that you can use to mutate the molecules that the agent generates and bias the generated molecules towards some area of chemical space that maybe you want to see more structures of. So we will play with this concept a little bit at the tutorial, but just so you know what it means. And then the last step, of course, is after training, generate a set of molecules. I think in this project we generated 100,000, we will see. Do retrosynthesis of this space and select some reactions that we can actually do in the lab and then test the compounds. So how did we actually do this? So in this paper, we really wanted to explore the different options that you would have in such a project. So we actually compared to a simple baseline where we have no synthetic accessibility score, Then we used very often used assay score by Ertl. And then we used the different machine learned scores. So what we wanted to see in this study is actually, does it matter if we are using in-house building blocks that really restrict the chemical space that we can access? And do we actually get more molecules and better optimize the QSAR objective with zinc building blocks that actually could lead to potentially larger space? So we generated 100,000 structures for each strategy, and we solved routes for all of the 6 cases. With AI Zinfiner, we determined the desirability of the generated structure. That means if it satisfies the model and if it's synthesizable, and then answer these questions. So how many desired compounds with solved routes can we actually obtain? So like molecules that we can obtain, but that are also predicted by the QSAR model as positive. Now, the second question was, what was the prediction error of these machine learn-based scores on the generated molecules? Because these machine learned scores, they are trained on Campbell, for example, or like drug-like chemical space that we know, but generated molecules, they can come from different space. So then there will be some applicability domain issue. So we wanted to also look at that. And last question, of course, already mentioned it. Can we actually pick and synthesize some compounds and then validate them that they are active on the monoglyceride lipase target? So question 1, let's take a look. So it was quite interesting to see that, yeah, if you use only QSAR, then you actually don't get very far in terms of synthetic accessibility. Because most of the structures, they might be predicted active by the model, but we are not able to actually solve the retrosynthetic routes. When you use assay score, that's good because you get a lot of molecules that you can solve, because assay score is really good at prioritizing very simple to synthesize molecules. But then we had a problem to actually optimize the second objective, which was activity. So if you then look at both synthetic accessibility and activity predictions, then you get not so many molecules actually. And then when we were using these machine learned scores, it was actually quite a good trade-off, in our opinion, to get both solvable molecules and both active molecules. So that was quite encouraging to actually see in this project. And a surprising thing was that actually it didn't matter if we used LED-free building blocks, which were in-house building blocks, or zinc building blocks. We still got comparable results from the generative method. Here's question number 2. So do we actually lose performance, the predictivity of these synthetic accessibility scores? And yes, we do. So since the generated space is a bit different than the training space, you will actually get lower performance scores. Remember that we actually solved the routes for all these 100,000 structures, so we were actually able to generate this data and look at how predictive the model was, whether we can solve a synthetic route or not. So that's kind of a take-home message. If you're using machine-learned synthetic accessibility score, you need to be careful that the performance will be a bit less. And in the end, yeah, we did some experimental validation of some of the compounds. And yeah, we only selected 3 of the set. And one was moderately active in an assay, so we count that as a success. And it was not a novel hit. It was quite similar to some already known structures, but it was still kind of interesting because medicinal chemists, they said they wouldn't really think of this modification. So that was a maybe nice idea from the AI. So another project that maybe I want to showcase really quick is my work on the chemokine receptors. So the chemokine receptors are quite interesting, especially because they have some role in metastasis of cancer when they facilitate, after activation, the transport of tumor cells into lymph nodes. So this is what you really don't want. They are GPCRs. The way they are activated is through basically binding of these chemokines on the outside of the cell, which leads to a conformational change, and then in-cell signaling like this. There are drugs that actually bind to the orthosteric site on the extracellular side, so to block the binding of the chemokines. But this is actually a little bit tricky site to target because it's very large. The chemokines, they are very non-specific, so they can still, even if there's a molecule here or there, they can still recognize part of it and still activate the enzyme. So competing with these chemokines is quite difficult. So there are some strategies. For example, you can look at allosteric modulation on the inside of the cell where you actually block where this G-alpha protein binds. So you can put a small molecule in this binding pocket and you can inhibit it this way. So this, there's a way to do this. And that's what basically we are focusing on, or the pharmacology group in Leiden they're focusing on, because this is still quite a new approach and there's not that many ligands known for this binding site. So that's what we did in this project. Again, same approach, same scheme, but this time we're using molecular docking because, like I said, we don't have a lot of information about structures to build a reliable QSAR model. So we use docking as one of the scoring functions, but otherwise it's the same to what I just described. So a little bit about the pocket. So this pocket is quite narrow, quite small. Probably the most distinct features of all the ligands that we looked at is that they form hydrogen bonds with this part of the pocket, but there's also some pi stacking interaction here. There's a lot of aromatic groups in this part, and then there's some lipophilic subpocket here, but also one that's not shown here, a bit here.
Můžete zůstat v budově, planý poplach. Můžete zůstat v budově, planý poplach.
So I guess we're back. It was a false alarm, as expected.
Sorry for the interruption.
Yeah, that's fine. That's fine. I'm almost done actually, so I'll just go fast through it. Yeah. But I have till 12, right? So 5 more minutes is fine. If we want 10 for a question. Even more, okay. Yeah. So, yeah, I already explained, so this is the pocket. These are some of the ligands. So what we did is basically we did some docking of all the most potent known compounds. And we looked at the overlaps in the pockets. I'm going to skip through this. Those are the different compounds. All you can do actually is maybe calculate interaction fingerprints of these compounds. So once you do docking, you look at what residues these compounds interact with. So we identify some common interacting residues. So basically, I constructed the scoring function in this case based on this information from 5 most active compounds from each scaffold group, which you can see here. Basically what residues they interacted with, and I weighted them to like required, essential, important, or interesting interactions. And then I did some weighted average of how many interactions of each kind we actually got. And that was the scoring that we used. Of course, depending on what you actually look at. I only looked at the 5 most active scaffolds, but if you look at maybe all active or moderately active compounds, you get slightly different ranking, but it still is quite similar. So in the end, we trained this DrugX model. So I show this is some data from the training, but most important is actually this desired ratio. So in the end, we ended up with like 40% of satisfactory molecules that were both synthetically accessible to some extent, and the score was good. Then I did generate 10,000 molecules and did some more stringent filter and ended up with 96, really top scoring, like most synthesizable and most interesting structures to actually look at by hand. And after some manual prioritization, clustering, things like that, we ended up with basically 4 distinct scaffolds that we wanted to make in the lab. So that's what I'm going to summarize next. We did some molecular dynamics experiments on these scaffolds. So this is just how it looks like for the reference. So these are the hydrogen bonds that I was talking about. Here's some other interactions. So this is basically the reference ligand that we wanted to compare our ligands to, and also the trajectory. So for like one candidate, we actually got similar interactions. The trajectory was also somewhat stable, RMSD of 1.8, I think, so that's fine. There is some fluctuation at the end of this trajectory, mostly due to this, but the core of the structure actually stayed very stable. And again, interactions very similar to the reference compound. So this is just another compound that we looked at. Again, looks good in terms of RMSD, and interactions are the same. And we also got experimental data for some compounds. So I only show you like sort of the 2 best, most interesting compounds, but we actually made more of these compounds. So I can show these. This was actually quite an interesting case where we observed interesting scaffold hop or some novel idea from the model where the closest compound from the training data was actually not measured on CCR2, but a different one. So we also did that measurement. But this was quite a novel scaffold. It was had kind of a similar activity. So it was kind of interesting to see the model generate something that's really like somewhat new, but still works. And it's quite obvious why it works, but it was just an interesting idea. And then we have so those are these compounds over here. And then we had some actually moderately good binder and one actually quite surprisingly good binder for very new scaffolds. So I'm not showing these structures yet because we don't know what we want to do next with them. But for this one, for the V400D5, which is this curve here, no, the D5U, sorry, the Ki in 100 nanomolar Ki was actually quite a good result for very novel scaffold. So again, we did the whole thing. Like in the previous project, I just wanted to highlight that we're developing these tools so that they are very easily doable, so that you can execute this workflow on basically any target that you wish and analyze the results more easily. So this is more for the tutorial. And some quick conclusions. So de novo drug design is a large and historically rich field. Definitely it has seen a significant boost in how creative people are about it, especially in terms of generative deep learning. Main challenges are synthetic accessibility, which hinders actually how we go from these virtual generated compounds to the lab and to testing. And we need definitely better validation and benchmarking, which the group in Prague is also working on at the moment. And I would really emphasize that prospective validation with follow-up wet lab experiments is really paramount to actually get some feedback on how successful these generative algorithms are. And to me, especially beneficial is to get feedback from medicinal chemists, show them the structures, discuss how they are good, bad, what we can do better. And I would say that maybe underexplored area is this multi-model and zero-shot prediction model, because with these deep learning architectures, you can really do a lot of things and combine very vast kinds of data from from maybe even genomic data or data on related targets, sequence data, things like that. So I would say maybe like de-orphanizing proteins with such an approach might not be a bad idea. But in the end, the experience of using a molecular generator is usually like this. So you have some machine learning system or an algorithm, you pour some data into it, then you stir it until you get the right answers. And that's my experience with working with generators, actually. So yeah, thank you, everyone. And now it's time for questions. If you want to check out the tools, just this is our GitHub.
We have plenty of time for questions.
So maybe if there are no questions, I would like to open the discussion with something which I wondered about for a long time. So how come it's the case that many of these contemporary generators are based on smiles line notation and not on graphs? Because of course we have the problem of canonization, several smiles goes onto the same molecules, but still they perform that. So
I would say that's mainly historical, because like the RNN architecture comes from natural language processing. So yeah, smiles is the language of molecules, right? So people just take that. But it's not the best approach, of course, because in order for the generator to do something useful, they need to decipher the syntax of smiles, in addition to seeing some chemical information in there. So that's the major challenge. But there are also, like, for example, in DrugX, we have this graph-based transformer model that actually uses the graphs of molecules. So there are like some approaches that use graphs, but yeah, you're right that people still use smiles a lot of the time, or some variety. And I think it's more historical, but also the fact that even though it has some obvious problems, like you mentioned, they still work okay. So yeah. Yeah, there was a question.
After molecular generation, we know its physical-chemical properties, but how do you assess its synthetic accessibility? Because
yeah. So like I mentioned in one of the projects, we trained basically QSAR-like models to predict synthetic accessibility. So you have this. Maybe do you know AI Finder? It's a retrosynthetic prediction tool. So what you can do, for example, you can take clustered data from Campbell, maybe like 1 million structures, and you run AI Finder on it. And then you get, for some of them, you manage with your building blocks to find retrosynthetic paths. With some, you don't. And then that's your training data. So you label compounds, okay, I can, with my building block set, I can make these synthesizable, I can synthesize those. I might not be able to get those. So again, it's still a prediction on top of a prediction, but it can still weed out some molecules that maybe are based on building blocks that you don't have available or you cannot purchase. So then you can use this prediction in the model to inform it. Yeah.
Other questions?
How much experimental actual data you need to actually start things?
It depends. Like I said, for example, in the CCR2 example, we only had knowledge of a few active scaffolds. So if you can do reasonably plausible docking experiments, maybe validated with some MD simulations, you can already include that in the model. That's what's very nice about reinforcement learning, because you can really shape the objective function so that you understand it. So at least that aspect of the model you can understand better. So even with little data, you can more understand the limitations and based on the results that you get. So you can adjust the objective. So I would say every project will be a bit different. But like I mentioned, in these zero-shot projects where maybe you have a completely orphaned protein, it can still give maybe some plausible ideas for compounds based on like the similarity of the sequences of related proteins that are within the model. And then you don't need anything. But again, like we saw, the generalization of that kind of model is not very good. So depends really how related your protein is to what it trained on. Yeah.
A question regarding the comparison of these recurrent neural
told that recurrent is still more popular than transformers, but are there just historical reasons, or they're really better than transformers, faster, easier?
Yeah, they are faster, way faster. And I would say that, again, in drug discovery, we have very small data sets. So it's also a problem with this, that the more complex model you use, the more problematic it becomes with small data. So yeah, we do have a transformer architecture, 2 of them actually. One is language-based, like based on smiles, one is graph-based. And yeah, it takes a long time to train. It's more finicky in terms of the optimizer, because you need to use a scheduler to train a transformer. So I think that's one of the reasons. Then, yeah, small data set size and also historical, because a lot of people use reinvent, which is RNN based, and it works okay. So yeah, that's probably. But yeah, regarding the outputs, you can get quite different outputs, I would say. But this holds for all generators actually. If you keep the objective the same, and you use different generators to generate set, there's almost 0 overlap. So that's also somewhat trained on the same data, because they are different approaches. They take different things from the data to incorporate. So it makes sense, but it's really hard. That's why I said this benchmarking and validation is a big issue, because there's no clear way how you should say one generator is better over the other.
If you ask 10 people to draw a duck, they would be different.
Yeah, exactly.
So how can you assess the quality of your generator if you will invent something new,
Yeah.
if you can't compare with the previous?
Yeah, well, just prospective validation is the best. Just using it in practice, seeing, talking with medicinal chemists, and putting that feedback to developing the model. But there are also more systematic approaches, of course, you can use, like a rediscovery, like something like a time split, like rediscovery of scaffolds in your generated set. So you can look at that. Of course, some general measures like diversity, distributions of descriptors, if the distribution of descriptors in your generated set is somewhat similar to the starting set. But then, of course, like if you're optimizing ADME properties, you actually want that to be different. So it again depends. Yeah.
Some other questions? No. So thank you, Martin, once more.
Thanks.